Okay, I'm Tim Ventura, and welcome to another edition of APEC, the APEC conference. This is December 12th, 2020. I am extremely pleased to have so many people here. We have a lot of folks coming back again. And today we're starting out with a presentation by Gary Stephenson. Gary's going to be talking about high-frequency gravitational waves, as well as some basically some new data that he has that goes along with that. And then we'll do a Q&A session after that, and he'll be followed by Todd Desiato, who's going to be talking about quantum atomic resonance effects and how those might be leveraged for gravity modification. So again, welcome everyone. The APEC rules are we try and keep everyone muted at all times. Raise your hand. I mean, you can literally raise your hand. Raise your hand in chat. Entering questions in chat is a great way if you have questions and you want to talk. And that just kind of helps us keep things organized. So without further ado, let me hand you over to Gary Stephenson, who has decades of experience working closely with Bob Baker, who was really one of the innovators that launched high frequency gravity wave research. And Gary has done tons of his own research as well on this. Okay, so Gary, I am unmuting you now. Thank you, sir.
Great. So when Tim asked me to do this, I put together a summary of the gravitational work I've done over the last couple of decades. And he was very polite when he got it, but he was like, you know, my people are kind of like more hardware people. You know, he didn't say, where's the beef? He was very polite about it. But could you add a little more hardware? So that's why I have hardware edition in here. I'm not a day-to-day researcher in gravitational work. My day job is aerospace systems engineer. But since getting my undergrad in physics, I've always maintained an interest in gravity. And so I've always tried to keep a toehold in the field. So I'm more of a gadfly or a spectator, but I do publish about once a year or so. So in my talk, I'll give a little timeline of the work I've done. I'll point out some highlights, but really what I want to focus on is what I think are still areas of interest that really haven't been explored as much as maybe they should be. And so I'll cover a couple different things. I've got a son that has the annoying thing of saying, is that a thing? Or that's not really a thing, is it? And so these, I think, are things. These are things that we should be interested in. The first two kind of go together, thing one and thing two, detection of high frequency gravity waves and generation. Because if you have both those pieces and you have them in a lab, then you've got a gravitics lab. And you can test materials with that lab. And you can find out more about, are there index of refraction materials available for gravity? Clive Woods has written on that. Are there metamaterials that help amplify or help change the coupling between the stress energy tensor and the warp of space-time, the Ricci tensor? And Jack Sarfatti says there are. But we won't know any of that without a gravitics lab that has a generator and a detector, so we can test these materials to see what the effects are. So I really want to advocate for that, and I really think those are things. The third thing I want to cover is a scalar field propulsion. There are a number of different techniques I want to really focus on Robert Forward's concept. And then I want to focus too on the Tic Tac tech, what changes might be afoot if Jack Sarfatti is right about how Tic Tacs work and how that technology might really help with this other work. Then I'll polish my crystal ball at the end of this and give my predictions. The future is probability space, but I'll point out the things that I would love to see happen and see if we can tilt the tables in that direction. These are the first half of a list of my publications, and have a look through these. And if you see things that I haven't talked about that you want to talk about, feel free to throw them in the chat window. We can address them after the talk. I really only want to spend about 40 minutes on the talk and leave the rest of it for Q&A. The things I want to highlight here are the first International High Frequency Wave Gravity Workshop held by Mitre in McLean, Virginia in 2003. There was a second one that was hosted by EarthTech, Hal Puthoff in Austin, Texas in 2007. And then there was a third one hosted by Fangyi Li at Chongqing University in China, 2017. So I like those workshops because when you get a lot of ideas together, a lot of engineers and scientists together, that's kind of when the magic happens. And so there's a lot of activity that went on surrounding those workshops, both going into and supporting those workshops, and then coming out of those workshops after we discussed them, papers that happened or discussions that happened that followed those up. And so I'll be alluding to those as we go through. The fourth one that I kind of wanted to highlight was this more recent one, Marcel Grossman 15, which happened in Rome, Italy in 2018. And this is where I presented a proposal for lab generation of a scalar field using a forward coil. And so I want to touch on, that's kind of theme 3. I wanted to touch on that a little bit too in this talk. Those are sort of the highlights. Theme 1. So first of all, why high gravity wave? Why high frequency gravity wave? The advantage there is that when you're looking at producing gravity waves, it's a quadrupole. It's the third derivative of a quadrupole moment. Okay, so not only does mass have to be changing, but mass has to be changing in a way that has a third derivative. And if the mass energy distribution is changing in a way that has a third derivative, then your stress energy tensor has a third derivative, and that can change the shape of space-time, right? That's the other side of the equation, is space-time equals the stress energy tensor with a coupling constant. And so the higher the frequency, the easier it is to get a gravity wave. If you're looking at low frequency gravity waves, you need to crash 2 black holes into each other to see a signal. It's a little easier if you have a high frequency gravity wave, because a lot of the effects when you work through the math goes as frequency to the 4th power. So you're getting that to the 4th power effect, which is very helpful. In this particular, so I looked at a number of these detectors when I first wrote a paper for the very first high frequency gravity wave conference at McLean, Virginia in 2003. I went through a whole series of detectors, and the one I thought was going to be the most sensitive was this Feng-Yu Lee design. It's become known in the West as the Lee-Baker design because Bob Baker has been such a strong advocate for this detector as well. And in this depiction, which is out of Physical Review D, the high frequency gravity wave is coming in from the bottom. And it's situated so that the high frequency gravity wave is coming in longitudinally through a sensor beam. This is an electric field beam that it's an E field, essentially, a static E field. And it's orthogonal to a static magnetic field. So you've got a B field, and then orthogonal to both those, kind of like a Lorentz force, like an E cross B, orthogonal to both those are perturbed photons. So you've got a lot of photons swimming around here, right? You've got the E field photons, you've got the B field photons, but when a high frequency gravity wave stretches that space-time in which these photons exist, it's perturbing some of those photons, and those perturbed photons go out in a symmetric way on a third axis. And so that's a huge benefit for when you're looking at a detection situation, because the detector on the plus x-axis might be noisy, the detector on the minus x-axis might be noisy. But when you see hits both here and here on 2 different detector sets, that's giving you a square root of 2 improvement in sensitivity, even for a stochastic signal. So that's a real nice detector orientation, and that is one of the reasons that everybody's been interested in that. The generic name for this kind of detector is 3-dimensional synchro resonance detector. There are other synchro resonance detectors. There's a 2-dimensional version called the Gershestein effect. This is a Russian that worked in the 60s, and he discovered that if you have the same arrangement and you run a gravitational wave in here, you get a synchro resonance set up where there's also going to be a signal, a photon signal that synchro resonates with the gravitational wave along the z-axis. The problem with that is it's in the same axis as the E field. So it's very difficult to measure that signal, and it's not nearly as sensitive. In fact, the Jasons in their review of the Gershestein effect said there's just no way it would work, in a terrestrial setting. This is a picture that came to us from Feng-Yu Lee of the same detector arrangement in the second high frequency gravity wave conference. It's interesting to see how this developed At the first HFGW conference, it was a cartoon. By the second one, we'd clearly had more of a simulation scheme going on here. And then I don't have a picture of it, but in the third International High Frequency Gravity Wave workshop, I saw, and I should have taken a picture of it because the paper hasn't been released, but I saw this same detector arrangement only in a very detailed CAD version. So it looked to me like they had done a very solid, very detailed CAD layout of this same detector. So it seems to me that they've been doing quite a lot of work on developing this design. Here in this instantiation, I suspect this was probably for simulation. I don't recognize what the 3D modeling is here, but we're looking at a 10 watt, 10 gigahertz sense beam. So we'd be tuning the sense beam for the frequency of the gravity waves for which we're looking. So, and you'll also notice right down here at the bottom, it says HFRGW. What we're doing here is we're looking for relic gravity waves, high frequency relic gravity waves. The relic gravity waves would be gravity waves coming from the Big Bang. Apparently the Big Bang was quite a noisy event in gravitational space. So those are still ringing around. And it presents a noise floor, and is one of the reasons we haven't gone forward with using high frequency gravity waves for comm, because the comm signals we can make right now are drowned out by the cosmic relic gravity waves. So in this instantiation, this particular detector is going to be looking for cosmological or astronomical type signals. So it doesn't need a generator to be able to make measurements. It's looking for natural sources. But you can see then the B field, 9 Tesla for anybody who makes magnets and that's a pretty stout B field, right? But it is doable. You see B fields of that order in MRI machines, for instance. Microwave detectors run down to 480 millikelvin, very high vacuum. So we're shrinking the noise there by getting rid of atmospheric Brownian motion. And then the Gaussian beam is really only 10 watts. When I first looked at this detector, I was saying we need more like a megawatt. But the reason we don't is this focusing element. It's called a fractal membrane that was added later to the design. And this is a focusing antenna, essentially, that will focus the detection photons onto the detectors. And this magnifies the effect quite greatly. And it makes it very, very much more sensitive when we use these fractal membranes. It's the same kind of antenna array. It's almost a metamaterial in a sense. Same kind of antenna array you might see in your cell phone. Notice that cell phones are flat. They used to have little antennas sticking out of them. They're flat now because the antenna is flat. It's a fractal membrane that's in your cell phone. And this is a similar kind of antenna. It's a flat, essentially phased array fractal membrane antenna that helps focus these detection photons. And so you get a huge magnification here, basically antenna gain because of that element. So this is my little hardware slide on how you might build one. And this is as far as really I have insight right now onto what the Chinese are doing on this detector design. I know that we're working with the high magnetization lab in China to get the green part of this built. I don't know how much their funding has happened since 2017, but in 2017, as I mentioned in Chongqing, they presented a very detailed design for this. Next part of this is lab generation of high frequency gravitational waves. And one of the schemes that historically has been looked at, Leonid Grishchik, who has passed since then, Grishchik and Sajin, his partner, both Russians, had schemed that you could use a toroid of resonating electromagnetic flux. So this is a pure energy toroid. And if you're going to use pure energy, it would have to be in the gigajoules per meter of resonating in a quadrupole moment. So you're kind of resonating like this, where you're squeezing the EM back and forth in a quadrupole moment, right? So you're compressing in this way and then compressing this way. And that creates that quadrature or quadrupole moment you need to propagate a gravitational wave. So you could use resonant energy that. So I took that idea and I said, well, what if instead of using E, we use E over C squared mass. So mass is C squared more likely to produce, mass movement is C squared more likely to produce a gravitational wave or more effective at producing a gravitational wave than energy. So if we can get plasma mass in a toroid, when I look at this donut, I think also of a tokamak. And can you get a tokamak resonating in that same pattern? They do resonate plasma all the time in order to stabilize it. And there are ways to do that. But as far as I know, it's never been attempted, at least not in an American tokamak. So here back in 2003, you'll notice this is the Fang Lee detector. It's a cartoon at this point. I was assuming a sense beam of megawatts, a B field strength of 30 Tesla, but it was 10 to the minus 33 strain sensitive instead to 10 to the minus 32, which is the current design. What is G wave amplitude? For those not schooled in the art, that's the amount of meters of change in a distance on an axis over the amount of meters. So 10 to the minus 33 meters of change in scale on an axis in 1 meter. Very, very small percentage-wise amount of metric change that's happening over a meter. But that's how they measure gravitational waves, is metric change over the metric. So that's on either axis. And as the gravitational wave propagates in transverse direction, the wave, and I think I have a video I can show that kind of shows this. The wave is shrinking and expanding space-time in alternating directions in a way that preserves momentum. The reason you can't have a regular sine wave, transverse wave in gravity is it doesn't preserve momentum. So the only way you can propagate a gravitational wave is in a way that preserves momentum, such as a quadrupole, octupole, or higher order. The very interesting thing about the last detection at LIGO was because the mass sizes were so mismatched, we saw very high order gravitational waves. They weren't just quadrupoles, they were octupoles, 16 poles, 32 poles. So kind of astonishing that we were able to see these higher order effects. All the designs I'm talking about are for quadrupoles, the lowest order effect. Here we see the inside of an example tokamak. This is the D3D General Atomics tokamak in San Diego. The Department of Energy uses this to experiment with new instrumentation. This is the best and most fully instrumented plasma experiment in the world. If they're working with sensors for plasmas, they test them out here first, and then they put them in ITAR second. So this is kind of our contribution to ITER, is testing these various plasma sensing schemes. This is one thing we could play with, since it's an experimental fusion tokamak, and try to repurpose it. The good news about tokamaks is they're already built. You're not starting from scratch. The bad news is they weren't built for this. They were built for making burning plasma. And so we would need to repurpose it. What would we need? We would for sure need these microwave excitation coils. So we're vibrating in a quadrupole way at microwave energies, enough plasma that we can make a gravity wave big enough that we can sense it. And if we're making that much microwaves, we're going to need shielding. We're also, because plasma sensors aren't used to operating at the kind of bandwidths and frequencies we're talking about, we would need upgrade to the plasma sensors. And then because these devices, the schematic of it, this is a simplified schematic of it. If you've ever looked at a fusion tokamak, they're a mess. They are complicated. There's not a lot of geometry room. It's pretty crowded. So we would need physical updates to move everything else out of the way of the things we want to add in. So there'd be a lot of changes to this, but you can see, inside here, it is a big device. There should be enough room to accommodate some of these changes, in terms of excitation coils. So there's some ideas. We would also want to accommodate the high frequency gravitational wave detector somewhere, probably immediately above, immediately below, or both, immediately above and below to make sure we're really picking up a real signal. And that would be then a working gravitics lab, right? Because we've got now a generator in close proximity with a sensor, as I showed here. And the other thing is we could put then samples of materials between this generator and this detector to say, hey, what does a metamaterial do for us? What does a superconductor do for this? I alluded before that Clive Woods, one of my associates that I've co-authored with in the past, has written papers about superconductors being able to focus gravitational waves. It is because they have an index of refraction in the gravitational permittivity. If that's true, that would be an enormous benefit, right? Because you could take then a big generator, focus the energy, and make a much stronger signal. There are some other ways to generate. So I think we can see if we can get this animation working. I'll have to access the web, and we'll see if we can get this going. And I hope you can hear the audio.
The first gravitational wave generator option uses micro-electromechanical system actuators for impulse generation. Known bulk acoustic resonators are triggered to jerk in unison. They are aggregated in two arrays represented here as blue squares, generating gravitational waves on the focal point at the axis of rotation. At the focal point, we see the characteristic distribution pattern predicted by general relativity, with the oscillating red squares representing the oscillations of space-time that constitute gravitational waves. The detector accepts the gravitational wave along an axis stimulated by EM and immersed in a magnetic field, emitting detection photons perpendicular to the axis of travel. The next gravitational wave generator option uses X-ray lasers for impulse generation. Each X-ray laser fires a short, strong X-ray pulse, which impacts the X-ray target to create a third derivative of motion needed for the generation of gravitational waves. A pair of X-ray lasers is used in unison to develop the gravitational waves at the central focal point. Gravitational waves are again represented as red boxes, with X and Y axes of the metric taking turns stretching and shrinking. The same detector is shown in this case, with the signal photon triggering a sensitive quantum detector to register an output signal. A frequency time standard is a possible early application. A single gravitational wave generator could be used to time synchronize any number of remote detectors, even those in orbit. The detection leading edge can be very tightly controlled, as gravitational waves always follow geodesics and are relatively insensitive to index variations and interference sources. For more information on gravitational wave products, contact Circuline Consulting.
My thanks to my cousin Catlin for producing that video very inexpensively, because she was just hanging out before she got her lynda.com job on training videos, and so I got a really good deal on it. Okay, the third thing I want to discuss is production of a scalar gravitational field. This is cut from a paper I presented at Marcel Grossman. General Relativity Conference is given every 2 years essentially for mostly theoretical physicists, but they also do present LIGO results and experimental results at the same conference. So it was a good conference to go to get critical feedback, and I really appreciated them allowing me to present such a far-fetched design to a group of really august physicists. This was a paper, it was based on a paper by Forward in 1962, in which he knew at the time there wasn't going to be a technology that could support this design. But it's based on the lens thirring effect, where if you have mass flow running around this toroid and it's in spiraling, the frame dragging tends to concentrate more on the inside than on the outside. And that's purely geometry. It's because there's less room on the inside of a toroid than there is on the outside of a toroid. And you could wind it even more tightly so there's very little room on the inside, and really strengthen that scalar field, acceleration field that's developed on the inside. You can imagine a craft too that is sized so that there's very little skin of the craft on the outside of the coil. So there's no downward or very little downward force happening because of this lens throwing effect on the outside, even though essentially the lines of gravitational flux are the same on the outside and the inside, but that the vast majority of the mass of the craft is occupying the inside of the coil, not the outside of the coil. So this is one design for, how do we make our own flying saucer or saucer-shaped craft? Unfortunately, using current technology, there's no way to get it off the ground. You can't make 1G with current technology. If you do the numbers here, and Forward's equation for this toroidal development of gravitational force depends upon the derivative of the stress energy tensor, the radius, the internal radius, cross-sectional radius, as long as the outer radius of the toroid, and n is the number of turns. So if you get a nanowire going that carries a superconducting nanowire that carries a lot of currents, this could be measurable. And that was the premise of my paper. It could be measurable in a laboratory setting with a 10 meter device. This scaling factor, a gravitomagnetic permeability, isn't the scaling factor you see very often. It's essentially the coupling constant between the stress energy tensor and the space-time the space-time warp. So this is you can factor this into the G over C to the fourth typical term, which is n sub 0, and n sub r. It depends upon what the mass is in here, and we don't know what mu sub r's are. Sorry, they're eta sub r's. We don't know what this value is, and that's one of the reasons to have a gravitics lab, is to be able to measure that, because that will impact the effectiveness of our device potentially very substantially. Now, I'll go over in a second how Jack Sarfatti has looked at metamaterials that can affect this in a very large way, or even in a negative way, for essentially inverse gravity, right? Repulsive gravity instead of attractive gravity. If you can get a negative index material, you can get repulsive gravity. So that's what I presented at Marcel Grossman. When I actually read this paper decades ago, but when I had been studying for energy storage, superconducting magnetic energy storage devices, they started looking like this to me. And so this looks like high-powered superconducting magnetic energy storage, or SMES device. These SMES devices have been under development by the DOE. There was a program before the Trump administration at Brookhaven to build one of these. I don't know if it was Obama or Trump that canceled the program, but it's now been mothballed. But certainly that could be restarted at Brookhaven. It would be very interesting to see not just whether they could make a good size SMAS, but whether they could use it for gravitational wave generation. So the other thing to keep in mind here is that SMAS, you want a core that's high permeability for SMAS, because you're storing energy in the magnetic field. But for this application, you don't want that, because the more current you have, the larger the magnetic field, and you start getting Lorentz forces that start trying to rip apart the machine. So it's better actually to have a vacuum or an air core for an SMES that's being used for gravitational waves. And then where you put your material, your effective material that concentrates the lines of flux, would be in the center of the toroid. This is completely different than electronics, right? Because this isn't where the electrical field is. The electrical field is on the inside of the torus, but the gravitomagnetic field is in the middle of the torus. That's something to bear in mind when you're using these things. How to build one? I have a lot of gory details. There's two versions of this paper. I have a lot of gory details, not in the Marcel Grossman version, which is a 7-page version. I have another 20 or 21-page version that was published in 2019 that has all these build details. Marcel Grossman limited my page count to 7 pages. So it didn't have the design details, but I also published in a Chinese journal, the gory detailed one that has the extra 14 pages of design details. So I can recommend that 2019 paper to you. And the link is in my list of publications at the beginning of the talk. So that's the scalar part. Now imagine using that same coil, but in a segmented way. Here I show the segments. For instance, you can cut this into 16 segments, build those segments separately, and then connect them together later on if you've got superconducting connectors, which are tough to come by right now. But presumably you could do this in segments. If you do this in segments and don't connect them together and energize them independently, you can energize them in quadrature such that you are not necessarily operating them all on the in-spiraling direction, but some of them in-spiraling and some of them out-spiraling, such as you're doing a quadrature. And if you get that, and you're able to sinusoidally inverse that quadrature current, so you've got a sinusoid that's, these two are in phase, these two are out of phase, then you can get that third derivative of a quadrupole moment, and you can get a gravitational wave distribution that looks kind of like this pattern. So you can get gravitational field pattern in a snapshot in time that looks like this pattern, but alternates up and down and back and forth. And that pattern will help create a gravitational wave. This might be an easier way to build a generator than either the generators shown in the animation or a generator using a tokamak. So this is yet a fourth way here to generate gravitational waves. By the way, since that publication came out, the two generations in that animation, the second one, the X-ray laser one, has come under criticism because there's no material that will stand up to the impulse force of an X-ray laser that will be able to maintain its integrity in mass enough to jerk in a sharp enough way to create a gravitational wave. So I think the X-ray laser one is probably not going to work. The MEMS devices, you would need a field, like an acre of SMEMS devices to be able to make the SMEMS, sorry, the MEMS device work. Okay, that brings me to the fourth part of my paper on Tic Tac technology. Tic Tac is a euphemism for those not familiar with it, that is used as a nickname for, some call them UFOs, some call them UAPs, a UFO, unidentified flying object, UAPs, unexplained aerial phenomena. The reason people don't like the term UFO is we're not even sure if they're objects. We could be looking at a wormhole or a hole in space-time, which isn't really an object per se. And it doesn't look like it's flying, right? It doesn't look like it needs aerodynamics. In fact, quite the opposite. These devices tend to ignore aerodynamics. So it's not really flying per se. So that's why the more modern term is unexplained aerial phenomena. I don't want to get hung up on technology. Whatever you want to call it, it was tracked by an F-18 using an advanced targeting FLIR. This is a pod that's used for sensing and tracking and targeting of other aircraft. And those pods were mounted on, sadly, unarmed F-18s. It would have been very interesting to pop a shot off. They were unarmed and had only these pods because they were set up for training missions. They deployed off the USS Nimitz in 2004. This was discussed by Hal Puthoff in a 2018 talk, which I'll show a link here. I'll just give a very brief discussion on why this was an interesting sighting. Two reasons, really. First is this AT FLIR formed a track on it. It has a low light level camera and also an infrared camera in it. Both of those were able to form a track. The laser designator was not able to get a return So for whatever reason, light doesn't bounce off of this thing. But as a black hole in space, 2 out of the 3 systems were able to form a track on it. So we knew we weren't just looking at phenomenology or swamp gas. This was a real thing. The first important thing. Second important thing is we discuss intent. As discussed, I don't know how much Hal goes into it. I know I have a talk later that's linked that's come out very recently last week in which the Milburn report was being discussed. And they talked about some of the deployment activities of these F-18s. And one of the deployment activities was they had to rendezvous at a cap point. I believe that stands for combat assembly point or something like that. And it's a point at which all the aircraft have to rendezvous. And when the order was given to rendezvous at the cap point, the UFO moved to the cap point at a very great acceleration before any of the aircraft had a chance to react, which clearly shows intent. So we have, number one, it's a real object. Number two, we have intent. That's what made this sighting so alarming. And that's what really set off the Joint Chiefs of Staff. And they absolutely had a cow over this. And they decided, hey, we've got to get this out here. And we've got to figure out what's going on with this device. And I'm sure there was an internal investigation to make sure we weren't shooting ourselves in the foot. But it's beyond belief to me that some DOE-Q program or some dark DOD program would intentionally interfere with a military operation and put their aircraft in the way of a combat assembly point. It's impossible to conceive, because whoever would have given that order would have been drawn and cornered and had the pieces shot for treason by the Joint Chiefs. So it's not one of ours, is what I'm trying to say. It's also inconceivable that the Chinese or Russians would have this type of technology and not use it to invade Crimea and not use it to invade Taiwan, right? They have too many military objectives. It would be too easy to take care of if they had this technology. So all the fairy tales we've been telling ourselves about might be one of our dark programs or it might be foreign tech. It just, for this particular scenario, all of those arguments lost plausibility. So that's what made it especially fascinating and for the Joint Chiefs especially troubling. So there was a move afoot to release this more widely to try to get input and ideas on just what the heck is going on. It was released to the History Channel, the footage. And so I have a picture of that here. What got my attention was last November, I subscribed to Aerospace America because I'm a member of AIAA, and this was their cover story. Typically, UFOs don't make the cover of AIAA, right? This is the most credible journal that there is in the United States for aerospace. So that caught my attention. Jack Sarfatti has theorized, he has been working for HAL for many years on unexplained aerial phenomena. He has theorized, based on some of the phenomenology, that the skin of these UAPs are metamaterials, and I'll show in the next slide why he believes that. And you can imagine too, I won't say this is how Tic Tacs work. I'll say if I had to build one, this is how they would work. I would use forward coils for the up, down, forward, back, left, right kind of motions. And perhaps I might like to use metamaterials to strengthen the effects of those forward coils. But here's something else I want to propose to you, and it wouldn't necessarily have to be a forward coil. If it was a smart skin, you might be able to do the same thing. Who's heard of the Lenz's law? Lenz's law says, if you have a magnetic field, thank you, see some hands. If you have a magnetic field, a magnetic field, and you have something that you can create a current in, that the current that you're creating will oppose that magnetic field. And you can actually levitate devices this way. I saw a very impressive demonstration of this with an aluminum platter. It wasn't a magnetic material, it wasn't ferromagnetic. It was an aluminum platter that had current that was being developed in it by a magnetic field. And it literally, probably a 10-pound platter lifted off a table-size coil. That's Lenz's law in action. Now, the question is there a Lenz's law for gravitomagnetics? In other words, if you have a forward coil capable of maintaining enough current in it, then it can generate 1G of backwards countercurrent. Can you have such a forward coil, let's see if I can do this without flipping the page, such as this one, inside the craft or on the skin of the craft, to make Jack happy, that amount of current, that amount of countercurrent could be actually induced by the gravitational field of the Earth. If that's the case, then you don't need any power at all. It just starts floating. And that is somewhat consistent with some of the stories you hear, right, about these craft. It just floats there. It doesn't need any power. It doesn't need any input power because its input power is provided by the gravitational field of the Earth itself. Furthermore, you could have a secondary forward coil that could be charged up with current using the charge, gravitational charge of the Earth. And you've got that induced current now, and you use that induced current as a power source for all your other forward coils that are also powering the craft. In other words, you don't need any other power. If you're in a strong gravitational field, it powers the craft all by itself. So that is something I wanted to raise up. I put that in the very last chart of my Marcel Grossman talk. It wasn't in the paper, it was in the chart set. And I got blank stares. I don't know that the physicists in the audience either knew Lenz's law or knew what to make of it, but I wanted to raise it up to you all here too, because I feel like you've got a lot of open minds here, and we'll see what happens if we can build one that can actually get up to 1G. But if we can, and we close loop it, in other words, we just short it out, so it's all one continuous coil, will it charge up? Be very interesting to find out. A little more on Jack. Who is Jack Sarfatti? He's a friend of Hal Puthoff's, who has been a researcher in this field for many years. If you don't even know who Hal Puthoff is, I'm not sure we can be friends. He has been working in this field for, well, twice as long as I have, at least, through SRI first, Stanford Research Institute. And then now he has EarthTech, his own storefront in Austin, Texas. There was a now famous talk given only a few months ago by Jack Sarfatti at the Estes Park lecture. Estes Park is held every couple of years. It's named after the place it's held in Colorado, but it's sponsored by some O'Neillians. I forget the name of the institute that sponsors it. But these O'Neillians are basically space fans. And so they're good enough to use some of their resources to sponsor this conference every couple of years on advanced propulsion techniques. So Jack went to one of these. Jack is one of those guys that doesn't quite settle down long enough to publish anything, but he has a lot of good ideas, and his talks are quite interesting. And so one of his talks, he was talking about the incompleteness of Einstein's field equation. So this is Einstein's field equation in blue, with the exception of the S. The S is new. That was Sarfatti named it after himself. But here you have the curvature of space-time on the left, and you have the organization of matter and energy on the right, and the scaling constant G over C to the fourth. And what this says is mass and energy in the universe give the universe its shape, give space-time its shape. In other words, the curvature of space-time is affected by mass and energy in very simple fundamental terms. And there's this very stiff scaling constant that says it takes a lot of mass and energy to get a little bit of curvature in space and time, either tensor curvature or scalar curvature. So how can we improve the situation? Well, what Sarfatti's breakthrough is he said, this is a great equation for point masses. This describes the universe for point masses, where masses are all at a point. And geometrically and mathematically, it's easiest to treat them like points because it's as if you concentrated all the mass in a point. The problem with that is you're never actually in the matter. If you're actually in matter, then the equation is not valid, because the equation assumes the speed of light never changes. And of course, we know, because of the index of materials, the speed of light does change. And so the coupling constant probably changes too. Why? Because gravity, scalar gravity, and gravitational waves all propagate at the speed of light. So if that's true, and you believe that, then you can write a zero-rank tensor called S that takes that into account, that takes material scaling due to the presence of matter into account. And if it behaves at all like light in an isotropic material, S will look like this. Now, this is permittivity and permeability, just plain old permittivity and permeability. Here's what Jack wrote. So index of material, N, is E and mu to the square root, right? That's index of refraction, essentially. So look at S. If you plug in N here, S is N to the 4th power over mu squared. Holy cow. If you have a high index material, you can get a 4th power effect. I mean, that's just huge, right? So say you have, now you are dividing by mu squared. So if you have high permeability material, you're only getting mu squared because it's mu to the 4th over mu squared. However, if you have high permittivity material, like a supercapacitor that has 10 to the 8th permittivity, now you've got an enormous effect. So 10 to the 8th to the 4th times 24. So the effects due to asymmetric capacitors, the effects because of superconductors, amplifying the effect of a gravitational impulse. Now you see directly where it's coming from. It's a direct formulation. And so now if we have a gravitics lab, we can start experimenting with these materials. We can prove that this S matrix, even for isotropic materials, we're not even talking metamaterials yet. These are just vanilla isotropic materials. We can prove the gravitational effects of these materials. And now instead of me needing billions of miles of superconducting nanowires, I can knock that 10 to the 9th down, another 10 to the 2nd, and even then my effect is 10 to the 12th bigger. So we're gonna have a very small device now, a very small forward coil, making a very large impact if we have these isotropic materials embedded in the core of those forward coils. That is why I wanted to bring up Sarfatti's work. This is just a little more detail on how did he get here. He got here because we saw in some of the footage what looked like phase shift. Phase shift in terms of light, which implied phase shift gravitationally. So Jack pulled out of this S term, this phase shift term. These two are still getting multiplied together, but also multiplied in here, a cosine of phase shift, where he's defining the phase shift this way through the tangent. So it's the arctangent of this thing over here is your phase shift. And he's saying that it's negative for repulsor over antigravity, which we saw at the tail, which means the Tic Tac being pushed away. And in the nose of the Tic Tac, we saw an attractive or positive phase shift where it tends to be going forward. So it based on the phenomenology, the Tic Tac appears to be using phase shift, which means gravitational redshift and blue shift. And so I think that's where Jack got this formulation. He was trying to formulate it in a way that the Tic Tac was using it, and then would describe the Tic Tac. By the way, the Nimitz is not the only sighting of these things. The Roosevelt sighting was a little bit clear. I don't know that all the details of the Roosevelt sighting have been released yet, but it tended to confirm the shape of these devices, which is cylindrical with hemispherical ends, hence the name Tic Tac, just from geometry. So far I haven't gotten anywhere. I haven't got any experiments that have done any good. I've studied a lot of things. I've kissed a lot of frogs. Nothing's turned out so far, but I think we're getting a lot closer now with this S matrix. I feel like if we went back to some of these ideas, we could potentially get them to work, or other investigators, such as some of them on the call, using other gravitational experimental techniques, using some of these either metamaterials or high permeability or high permittivity materials, could potentially confirm some of that. What I would like to see more of is true funded programs for the 3D SR 3D synchro resonance detector, a plasma tokamak or some other generator, maybe a segmented forward coil generator, and a real program for gravitomagnetic toroid scalar generation program. Could see, can we do this at least in a lab? I think that'd be something that would have a lot of value and help placate the public as to say, we're doing something. If we do 1 and 2 together, we already have a gravitics lab. because we have a generator and we have a detector. So we know when we're changing the environment, we're seeing, how does this impact? And then, as I pointed out just a moment ago, Sarfatti has this S term. We could really look at that S term and decide, is that a thing? On the Tic Tacs, there's a really good, it's long, it's not boring, a really good walkthrough of the Milburn report that came out that was funded by the Israelis, that was done by the Brits on basically the US UAP task force program. That's on a YouTube. I'll give you guys the link to this. And I'll post this. I can send this to Tim after the talk, because I don't think the old version of my talk had this link, because this link just literally came out days ago. But I think once you look through that, you'll be convinced too that this phenomenology is real. We don't know where it comes from or what it is, but it's certainly real. My opinion only, I don't know. I don't have a DOE Q clearance, but I think we're not doing enough. At least, if not nothing, not anything visible. I think, as Scott Fitzgerald said it best, the strongest guards are placed at the gateway of nothing. It's the condition of emptiness that's too shameful to be divulged. I think we're protecting this because we're not doing anything. And I think that's kind of too bad, because we could be doing quite a bit here. And I'm nothing against hobbyists. I'm a hobbyist myself. But why isn't the US government, doing more with gravitics work? Honestly, this is a little embarrassing. So I don't work for Battelle. I don't speak for them. I don't work for GOE. But honestly, we should have seen more after the last 50 years here. That is all I have. So I guess I'll stop sharing. And Tim, if you want to open up to questions, either through the chat window or means, I'm happy to take questions.
Gary, thank you so much. This was amazing. So let me do this before we do questions. Let me invite everybody to unmute, and we're going to give you a big round of applause. So ask all to unmute, and let's give Gary an enormous applause, everyone.